Okay. Don't forget to sign your name.
Mathematicians won the war. Mathematicians broke the Japanese codes and built the A-bomb. Mathematicians, like you. The stated goal of the Soviets is global communism. In medicine or economics, in technology or space, battle lines are being drawn. To triumph, we need results. Publishable, applicable results. Now, who among you will be the next Morse? The next Einstein? Who among you will be the vanguard of democracy, freedom, and discovery? Today, we bequeath America's future into your able hands. Welcome to Princeton, gentlemen.
Hi everyone, thank you for coming. I'm very excited to start this presentation. So we're going to talk today about what I think is one of the most interesting subjects that is now also getting a lot of attention. It's like a hot topic. So AI for algorithms and mathematics discovery. We must begin with the latest drama. Just 6 days ago, OpenAI published a paper about their disproof of a conjecture made by Paul Erdos, and they've been doing it with their newest model. Just 1 day later, also DeepMind published they could solve 9 new unsolved problems by the same Paul Erdos. So this is just from 4 or 5 days ago, depends on how you count when you consider it published. So you can see that the big companies that are now in this AI race are trying to solve this apparently very important benchmark that Paul Erdos created with his very curious and fertile mind. So there's a lot of money at stake. That's a very good reason to to try and understand what's going on here, and also, of course, our self-esteem as mathematicians and computer scientists. What is our role if in the near future AI tools will be the one that really doing the big discoveries. So we will try to, in this presentation, we will review 3 interesting papers that are concerning this, that been able to arrive to new results with AI tools, and also we will look on the history. And I hope that from a more educated point of view, when you see these kind of headlines, you'll have more information and you can judge better. So let's educate ourselves. Let's start with a nice story. So you can see this is a paper that was submitted to the Journal of Symbolic Logic and was rejected. Don't try to read it, it is just an AI illustration, so it's not real text. But pay attention to the writers. The first, Alan Newell, the second, Herbert A. Simon, 2 nice men, and the third mysterious writer, the logic theorist, who is maybe a very mysterious person that doesn't like to reveal himself. We'll discover soon. They sent a paper. What was it? Wasn't even a paper. It was a scientific note. And what was this note about? They could prove the theorem number 2.85 in the book Principia Mathematica, that was written also by Bertrand Russell, the one who found the paradox in the original set theory. So he wrote a book with Alfred North Whitehead, and they wrote, it was like very proper theorems and proofs, some perfect mathematics. And the paper this not really a paper, that was also rejected. They could show better proof, like shorter proof, something that looks better. Okay, what was the story of those two men? They wanted to create a tool for automated proofs. So they had this idea of taking this Principia Mathematica, take the known axioms and the target theorem, then doing some process, some automated process in order to get to a proof. What was what was new in their approach? So you can do it in a brute force way. You can start with axioms, which are actually just strings of text that you consider to be true propositions. And then you can use all of your deduction rules and create some sort of a tree, and it will just grow exponentially, but you potentially can find anything which is real. But it is very expensive, it is brute force, and not necessarily you'll ever arrive to anything interesting. So what they've been doing is that they've been working backwards from the goal back to the axioms. They've tried to do it also with heuristics, and in order to make it something sensible. So let's look on one specific target theorem. This is a theorem, we can call it the goal. There's a proposition P. The goal says P. If P implies that not P...
There are several hundred prepositions in the English language, all of which are used to show a relationship
Coming to replace us.
Yes.
This is from yourdictionary.com.
It never happened to me before. Never. Okay. What can I do? Okay. We have this specific proposition. I never said this is the only proposition in the world. Okay. This one is the proposition that we want to prove. And this in the right is the axiom that we want to use. You can see that they are not in the exact same, it's not the exact same string. So I can't just replace the A is a variable or a placeholder. I can't just plug in the P because it's not exactly the same thing. But I can use some tactic or some truth that I know, that saying that X implies Y is the same as saying that not X or Y. So once I translate my proposition, P implies not P into not P or not P, in which I plug P into X and not P into Y, I can have my goal now exactly like the axiom, and then I can just replace the placeholder A and plug into it the P, and I finished, I did it. So this is an automated way, and you can see that I started from the goal and I went upwards into the axioms. They called it the logic theorist, so it's not a mysterious mathematician, it is just a computer code. And they actually presented it in the first artificial intelligence conference, at least the first conference in which artificial intelligence was the name that was used for this whole idea of AI. It was they showed their logic theorist, and it was the only computer program that actually worked in this conference. The rest of the things were more theoretical, some ideas, some proofs, but they actually had a code that could prove things. Okay, what they thought after they could, maybe I'll go back. I just want to say that the whole story with the paper was that they could prove this nicer theorem with the logic theorist. So they found with a computer a better proof for something. So after they made that, they were very excited, and Simon, one of the writers, he predicted that within 10 years some computer program will just beat chess champion. Within 10 years there will be a very major new mathematical discovery, and psychology will be completely replaced by computer programs, and machines will be capable of any human work by 1975. Sounds familiar to you? This is what they say. Anyway, back at the time, 1956, they were rejected because it was not cool enough that a computer program wrote a paper. Very sad. Okay, let's go. Why they were rejected? Because it was not anything new. It was a known theorem. They just found a nicer proof. It's not good enough for the journal. So let's look on one of the famous next steps. The four-color theorem. This was an open problem that was posed by Francis Guthrie. I think he was an English botanist. And he one day could observe that he can color the map of counties of England with just four colors in a manner that wouldn't enable any to border share the counties to also share color. And he was wondering whether this is only because England is so nicely ordered, or is it true for any possible map? So we asked that, and nobody could answer, and it was an open problem for about 125 years. I have enough time? Okay, very shortly. The way that in 1976, I think it was solved, it was solved with a computer. The mathematicians or computer scientists, they said, okay, let's prove by contradiction if there was any counterexample, any map that you must color with 5 colors at least, then it must consist of one of this huge number, 1,834 specific cases, and a case is like a sub-map. Let's think that this counterexample exists, and we will choose the minimal one. The minimal one must have one of those cases. Each case is reducible, meaning that if I take out one part, I can still, and this little part can be colored with 4 colors. If I take it out, I can still color it with 4 colors. And okay, I'm not saying it perfectly because we don't have enough time. Anyway, just there are 2 parts for this proof, okay? One is proving that any contradiction will include 183 and 1834 specific cases, and also that each case is reducible. So, for the part that all counterexamples must have at least one of those many cases, this they've done by hand. They wrote 400 pages, and then the mathematicians reviewed it, and they said, yes, we can prove that in the regular way that mathematicians are working, but the proof that each of the cases was reducible, this they've done with computer code, and because computers might have bugs and problems, not all of the community really believed that it was true, and every map can be colored with only 4 colors. But later on, 2005, George Gonthier, which actually has a very similar name to the one Gouthier that posed this whole question, he could verify that indeed the proof with a computer program was valid with a formalized with a language for formal verification, and then the whole community said, okay, we accept that indeed we can color every map with 4 colors. So this is the history. We looked at the logic theorist, the 4-color theorem, and formalizing the 4-color theorem, and now we will discuss our first specific paper from the AI era 2024. Alpha geometry. Pay attention, it was published on January 2024, but actually already sent to Nature on April 2023. So in our AI world with its crazy pace, it's ancient history, okay? But still we think it's a very interesting paper. So this paper is trying to solve some part of the International Mathematical Olympiad questions. This contest is something that started on the 50s. First country to host it was Romania, and it was just for the eastern part of Europe. But then it became global scale, more and more countries joined, and on the 2000s it became kind of a normal thing to send your smart kid into this Olympiad. So Terry Tao and Mariam Mirzakhani, 2 famous fields winners, they also been to the IMO. when they were younger. And now many AI tools want to solve this IMO, to be able to get a question and come with the answer and be as smart as those very smart high school students. So every IMO exam has part of algebra, many mathematic branches, and also geometry. Our paper tries to solve geometry. A geometry question looks like this. It's just text, you don't get the sketch. And then when you look on some dataset of solutions, you can find sketch and you can find nice explanation why everything works. And they want to be able to do it automatically, to get this text and being able to come up with a proof. Very difficult. Now you would say, why not just use ChatGPT? On 2024 it wouldn't work at all. Okay, also 2023 of course. So they must come with something else. Okay, maybe they can just use deduction tools. So a deduction is okay. Say that now I can use the laser. Yeah. If I want to prove that that this edge equals this edge, I can show that those two triangles are actually isomorphic by this very known angle edge theorem, rule, whatever, and yay, I could prove those are equal. I just did deduction. I had those three premises and I've been using this rule, very nice, I have it. Think about something that is more like, yes, okay, I have a final, when I have a geometric question, I have final set of points that I want to show that they have some properties, and I have final amount of predicates, of things I can say about those points, and I can choose 3 points and say they are on an equal edge triangle. I can choose 4 points and I can say they are on one circle or they're not. Those are predicates. There's a final amount of predicates, so overall I have final amount of things I can come up with and using the axioms in order to get from one step to the other. We will deduce and deduce, and we will halt somewhere, and we will just have the conclusion that we were asked for. Okay, I didn't stop at all for questions. Do you have questions? Good. It's perfect. Why not just deduce, okay? Here I have this. I say I'm in the IMO. I'm creating this nice sketch. Okay, I see that I have this premise that PQ is parallel to AB. There's also other premises, very interesting. I'm very smart, not me, of course, the deduction engine. And then I can come up with a final conclusion that I had to prove. Why not doing that? So deduction is not enough. Say that I want to prove that this right angle, this one, which is the complementary to this one, equals A plus C, the angle is A plus C, I must construct this line. Okay, I must use, I don't remember how, there's a rule about this angle and this angle. If those two lines are parallel, then those angles are equal. I must use it. This is a new construction that I've been using in order to show that. So it's not enough to just deduce, I must create clever constructions. And when you think about it, maybe one of the most important things in geometry questions is to be able to do those interesting constructions. So maybe what we should do is not only deduce, but maybe we can, if we will have more axioms, it will be enough. Because I showed you just this specific example, maybe I can have an axiom that every triangle have always a sum of 180 degrees. Maybe it's enough. Or if not that, maybe I can have some automate constructions with heuristics. Say I see that there is a triangle, I will always create the parallel lines in order to have all the needed points and lines and whatever needed for my deduction to have everything. And just a little note, pay attention that it is similar to our logic theorist, which is having some heuristics, which uses some heuristics in order to make the deduction clever, not just a tree. So maybe we should listen to our ancestors from the original AI in order to decide what to do. But I'm so sorry, it's not enough. When they tried to use just 18 heuristics, so they have many points that the question defined. They have all the possible things they can say about any subset of those points, and 18 heuristics for how to build some extra constructions. It's still not getting good results as the alpha geometry final neural architecture that we're going to discuss. They do need, you can see, for an example, this is another example in which you can see that there are, the red lines are constructions. I don't know what heuristic could be done in order to, I don't know, given this very, very, very specific case, build those red lines. No, it's not good enough. You can't do that. Because there are many, there's infinite amount of constructions you can make, unlike the finite set of points, finite set of predicates, and also you should be creative. Okay, I hope I convinced you that you can't just use heuristics in order to have those constructions. So what was the solution? Alpha geometry. As I showed you before, this had way better results. Now we will see how they did that. Their basic idea was, okay, let's get a problem statement. We will give this statement to some engine, neurosymbolic engine. It's only the symbolic engine actually at the beginning. It will deduce, it will halt, because there are final amount of points, there are final amount of predicates, it will halt. If it halted and I got my final proposition that I wanted to arrive to, I'm good, I can just say I solved it. But if not, I'm going to use a neural network that will create the next construction. And then after I have the next construction, I go again into the neurosymbolic. This time with the construction, I'm able to prove something that I couldn't prove before. Yeah.
So it's not only an AI, like you're using brute force to see all the possible...
Yes. I do a combination of AI and brute force, exactly. It's actually... you could do also a brute force in order to search for the next construction.
So why do you need like a neural model at first place?
Because it's too big. The space of possibilities for the next construction is too big. And when you think of this kind of question, of course, it's very easy. It's enough to do some brute force. You'll arrive to the correct construction. But I think this example shows you that in order to build those two lines, you should have some sort of, there's a good word for that, intuition. So you try to create an intuition. And it wouldn't, and the way they've done that is with a neural network. So the only role of yes?
And how do they verify once they get the correct proof or not correct proof?
They have a goal actually. Say, okay, in this, okay, this one, the goal was to find that Q1, P1, PQ are on a single circle. And this is a formalized statement, okay? Saying that 4 points are on a circle is something that you can get to with the deduction engine. But this deduction engine is final set of axioms and final set of points. It wouldn't arrive to this conclusion unless it has the needed constructions it needs to work with. Okay? There are many examples, but I chose to work. I think this one is the most simple I could think of a case that you want to prove something and you must construct something new in order to prove it. Okay? Does that answer your question? Okay. Da, 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 da. Yes. So yes, we are using a neural network in order to find those new constructions. Any other questions?
So what is the input and what are the output for the neural network?
Yes, so now we are arriving. This is I think the most interesting part. How you train neural network to have this intuition, to know what is the next construction that you should use. There is infinitely many constructions you can create. Of course, with those complicated IMO questions, you should have this intuition. So how you do it? Okay, just before I'm starting to explain about the data, some technical details. They didn't use some big model and fine-tune it. They trained it from scratch. And they took a basic transformer with 12 layers and 8 attention heads. Those are just technical details. They also used beam search, and maybe we can talk.
What is beam search?
Beam search. Maybe I will show more and then I will explain. So why it is you were asking about the data, how I train this model. Indeed, it's not easy, and one of the reasons is that geometry is not an easy subject in that sense, because formalizing geometry is more some sort of a niche inside of this community of formalization. So there were not like many examples of formalized theorems, premises, conjectures in geometry language. And Lean or Coq-Roq, they are languages which are more general, but back in the day they didn't have good enough representation for geometry. I think nowadays it might be different. So what they've done was they tried to create data points. How they did that? They sampled 1 billion premises. Premise is just, I think, this one is a nice premise, okay? Just ABC is a right triangle. Construct right triangle ABC. Okay, this is a premise. Another premise would be construct some X that will create the parallelogram around this ABC. Many premises, 1 billion of such, okay? Now when you have this general image in the head, we will go through into details. So this ABC, again, I'm explaining how we create this dataset. I'm not even touching a single data point. We're still creating some big tree of premises and deduction steps from which afterwards we will be able to get one data point. But we're still at the big tree. So the first premise can be ABC is a triangle. And okay, no problem, let's construct a triangle, then let's add the height and another height, and let's call the intersection with a name, and then let's create a line that goes from the top of the triangle through the intersection and meets the base. And then next thing I'm asking is to construct a circle that goes through those points. So A, H, F, you can see they're on a line. It couldn't happen that there's no circle in the world that can go through those 3 points. So, but I just sampled it randomly, right? So I sampled it. What can I do? Okay, so the deduction engine can recognize that this is not a legal move, and it will cancel this process of sampling. But let's assume that I didn't ask for something illegal. I just asked for the line that connects those 2 points, and here it is. Okay, fine. So I have now more complicated shape, and all of this is, think about a huge tree that is constructed just like that. Here is our example. Now we're going to touch a single point. How we're going to create a single data point. This time, so I have this big tree of constructions and also things I can say about I mean, after I created this shape, I can also say that that this nice shape is actually on a single circle. It's geometric thing that you learned in high school. I have this big tree. Now I want to have a specific data point, so I choose this one, this conclusion, HA perpendicular to BC. That the meaning is that there is a right angle here. I choose this one to be my data point. Okay?
I have one question.
Yes.
Just to understand, aside from the symbolic concepts, does the model actually generate a graphical interpretation of the layout and the...
No.
So it's only the symbolic...
Yes. I mean, you can do interpretability research and prove that somewhere in the neural network the weights somehow represent this nice sketch, but explicitly no.
Some of the layout information is actually encoded in the graphical interpretation, meaning the intersection points where one line falls on the other.
You're correct, and actually I think that there are some more classic tools that use this. How? They don't just define a point, they also give it a specific value for like the x and y of the point. And then all of the construction that it does, it gives some numerical specific values, and it looks for similar numerical values and tries to prove that those are actually the same point. It's more heuristic, okay? But in our case, no, they don't use it at all. Okay, so if I choose this point to be my final conclusion that I want to use as the basic data point, how I'm going to use it, I'm going to okay, this is not so crucial to show, but this is my final conclusion, and I'm going to build the minimal graph of deduction that I had to use in order to arrive to that conclusion. This is not the minimal graph, because here you have a specific premise that this point is the intersection of those lines. I can conclude that some angles are equal, but I don't need it for my specific conclusion. So actually, I don't have it in my minimal tree. How do I proceed from, maybe I will explain that as well. You can also see that the fact that these 4 points are on a cycle, since 2 points are E and D, I must construct this line ED in order to show that this shape is on a circle. So I put some mark over the conclusions that I had to construct new constructions in order to arrive to. And now, how do I create from all of this a data point? What do I want in this data point? Remember, we want to train a neural network. We want to train something that can create new constructions all the time. I would like to have each data point consist of premises, conclusion, auxiliary constructions, and then the deduction steps. Think that if the model will have to learn that after the conclusion it must first come up with the best new constructions, this is how we teach it to have intuition. So I take the premises, the blue premises from the top of the graph. I take the conclusion. Then I build the auxiliary construction, which is this line, build ED. Then I put all the deduction steps, and this is a data point. Okay? And now I have 1 million data points that I create that way. I had this huge tree of deduction. I chose each node that I want to create data point from as actually the basis for a minimal graph of deduction. Then I take the minimal graph, I understand which part of it is actually auxiliary constructions, which part of it is deduction, and then I rearrange everything and I have this nice big amount of data points that I am training with. Yes?
Is it annotated by humans? Like how you know like which is premises and which is conclusions? Like
No, no human at all. It is all synthetic.
So you also created the geometrical problems? Like how?
Yes. Okay. I just have 1 billion premises that I'm starting from, and I'm creating this tree of deduction. Once I choose a point that is a specific conclusion, I can look on the graph that created it. Which lives in the graph, now it is the opposite, right? Because I go backward. Which lives in the graph are actually mentioned in the final conclusion, and which are not. Those that are not mentioned, you can look at them as constructions. You understand? And so no human in the process, okay? I understand which axioms, which premises are not actually mentioned in the conclusion, and I use them as the auxiliary construction. So after I have this big amount of data points, 91% of them do not include any construction. I take some conclusion, I look for the minimal graph, and I see that everything that is written in the conclusion is, just in order to define my final destination, I need to use all of the premises. So in this case, I don't have any auxiliary construction. But in 9% of the cases, there was this auxiliary construction, and I care more about those examples because I want my model to be able to come up with constructions. I don't want it to deduce it all. For the deduction, I'm going to give it to the engine that does that and always halts and is deterministic and based on heuristics and is what once upon a time was the AI. So there are two phases for this training. I first pre-train with all of the data, then I use just the 9% of the auxiliary construction points, and I do fine-tune for them because I want the model to... Why do I do the first step? I want to teach the model how deduction works. I want it to have this kind of knowledge incorporated in the weights. But the extra construction are the things that I want it to always do. So in the end, I fine-tune it to always come up with a new construction. And so this is the framework that they've been imagined. The simple case, the real cases, the IMO questions, which are complicated, they look like this. In blue, they marked the auxiliary construction that their language model always generates. And look what nice results they've been able to achieve. Alpha geometry, the one in green or whatever color it is better than the silver medalist average score on geometric questions, and of course better than the state-of-the-art. This WOOS method, I didn't touch it at all. It uses polynomials, like something else complicated, but it could arrive to 10 correct questions from the 30. I didn't mention it before. There are many geometric questions in the IMO. They could take 30 that they could actually formalize with this engine that they've been working with. Okay? Yes?
What's the typical inference time from such a question? A single question in the IMO. How long does it take the alpha geometry to solve it? Roughly.
Good question. I don't remember. They discussed this issue. I think that in alpha geometry they didn't really try to say, oh, we can do it as fast as a student. It's a good issue.
Why it's interesting.
Yes, it's important. Later, they've been in later papers that they could achieve. On 2024, they actually also published Alpha Geometry 2, and they combined it with Alpha Proof, I think, and together they could arrive to better results. And then I think they also, better results. They could solve the whole IMO questionnaire, not only the geometry part. And I think that there they said something about the running time. Right now it's better. It's better than the human student, but not necessarily in this paper. So they had good results. And that's it. Another? I need to answer about the beam search. What do you have? Right? Okay. Any other questions before the beam search? Yes.
So is this 30 because this is the amount a student is asked a geometric question, or out of the whole data set, these are the only 30 that they could translate to the formal language?
This is the only 30 that they could translate to the formal language.
Isn't that a big limitation on what we can use this for? Why can't they translate the other ones?
It is a limitation. I think it was 75% of the whole amount.
Oh, okay.
It's not that small, but maybe I'm wrong. It is a limitation, but but it's not. If it was just I don't know, cherry picking the results that the alpha geometry can arrive to, then maybe it could solve all the 30 problems. But it wasn't the case, right? It was, yes, just the thing that they could formalize. Still, even though some questions have been formalized, it doesn't mean that alpha geometry could come up with the correct constructions, and since this is the case, they couldn't solve everything. But you are correct, it is a limitation. Yes?
I still don't understand what the output of the model, does it output pure text like ChatGPT, or does it output like lean code?
Okay, perfect question. It outputs text. It is fine-tuned and trained on something that always look like a text that is formal language, but it is text. It's just tokens. Okay?
So it's not guaranteed to be actually be type checked and be cool.
Right.
Yeah.
At least they don't say it is guaranteed to be that way, but this is the data set, yes. And also, maybe now I will touch the beam search thing. I don't have a sketch for that, so I'll try to explain.
The board. You can use the board if you
Perfect. What is the beam search? So I have this geometry question. It is some many things. I need to prove that there is a circle which I can mark on those 4 points that were somehow defined. Okay. First, I give it to the engine. If I could solve, finish, very nice. If not, I'm going to alpha geometry, the neural network neural network, and I am asking for the construction. So a construction is actually chaining of some tokens, right? Because a construction is create x such that It's not one token that can describe. So there are some amount of tokens, and I don't do it only once. I do it 32 times. I look on the highest scores. For the first token, I look on the 32 highest scores, and then I continue the process 32 times, and now I have many 32 constructions I can continue from. I give those 32 cases to the engine. It tries to prove again. If it proved, okay, finished. If it's not, I do again 32 constructions. Okay, 32 constructions. This time I have 32 multiplied by 32. I don't remember the exact number, but I'm not going to stay with everything. It's too much. I'm going to keep only 512. That's why the beam search size was 512. And then again I have 512 set of constructions. I give it to the engine. It looks for the result. If it could solve, okay, I finished. If not, then not. And it is important. I mean, when you reduce the amount of beam search, it does harm the results. This is not something specific to mathematics or AI. It's something general, this beam search thing.
But you could use like a random beam, right? Or you could use a smart beam. So
They base their beam on the score that the neural network give to each next token. You understand? Like they sum the amount of logits, and based on the maximum, or not the logits actually. No, they after the softmax, they sum the probabilities, and based on the biggest probability, they keep the specific 512 branches. So I think it's not.
So it's not random. It's
Yes. Yes. Yes.
Wait, I don't understand the logic behind continuing existing branches instead of doing new ones, because if all the 32 first branches are wrong, why the solution lies when
They're not wrong. They just didn't provide you with clever enough construction. You've been. It's too many slides ago, but imagine that there is. Is there any other color? No. Imagine that I need this construction and this construction and this construction, but I should be very creative and smart in order to get to those constructions. Only after I have those, I can give it to the to this engine that can deduce, and arrive to the final answer. So after having the first one, it doesn't mean that something is wrong. It's just not enough. Okay? Other questions? We're good? Okay, thank you. So this was the first part. And we'll
Take
have
a
a break.
Okay. Okay, we'll move to the second part of the lecture. Okay, so we noticed some very change, a big change in how you use models. Bye. Okay, so the stupid video era. Let's say until about a year ago, this is how you could see if a model is good or not, based on how Will Smith looks when he eats spaghetti. But now, solving big mathematical problems is how they present their newest model, which is pretty cool. Okay, so now I want to talk about something else. I want to talk about matrix multiplication. So it's, as we all know, we heard about it many times. It is used in many different fields. And when you count how many scalar multiplications you need in order to calculate this, let's say 2x2 matrices, you need 8 multiplications, and in 4x4 you need 64 multiplications, which is a lot. It's very heavy, it's very expensive. And in 1969, Strassen found some trick, and he was able to reduce the number of scalar multiplications to 49. But since then, 56 years later, it is still unbroken barrier. Still 49 is the benchmark for how many scalar multiplications you need. Until AI. Okay, so the next paper I'm going to present is AlphaEvolve. So we've seen all of our timeline, and now we are in 2025, which is just a year ago. But still, many things have happened since then, so you will see. Okay, so the goal of AlphaEvolve is to find new algorithms and improve old algorithms in math and in computer science. Okay, so it is like an evolutionary AI algorithm where the user defines some code and some evaluator. Then it uses Gemini 2.0 to propose changes in the algorithm. And then the algorithms that got the highest scores remain for the next generation. I will dive into it and explain everything.
Is it something like called genetic algorithms?
It's evolutionary AI. I didn't see the name genetic algorithms, but it's probably kind of the same. Okay, why can't I just ask Gemini, hi, find a better algorithm for matrix multiplication? because standard LLM prompting just returns existing algorithms. It wouldn't, in 2025, it wouldn't invent something new that it wasn't trained on. But in AlphaEvolve, which uses evolution, it's continuously creating like mutations in the algorithm in order to find brand new, unintuitive algorithms. Okay? Okay, so this is many things, but I think the most important thing to mention that AlphaEvolve is like innovative relatively to previous agents is that it could take like a whole program and not just like a function or couple lines of code, and it can do it in any language that you want. So it's like bigger scale. Now it looks like obvious, but it was a year ago, so it was different. Okay, so now we'll talk about how it works. So there is this scientist, which is the user, and this is AlphaEvolve. So there is this program database that consists of all the algorithms, and the user input is some initial algorithm. And the first step is to sample some algorithm from the database. The user also put an input to AlphaEvolve some prompts. So after it samples a program from the database, it also samples a prompt that takes the algorithm. Then AlphaEvolve takes some LLM, existing or some custom LLM, that creates some differences in the algorithm. Then there is just this child program with all the differences that the LLM created. And the user defines evaluation function. I think this is the most important thing. Like, for example, in matrix multiplication, you need to count how many scalar multiplication is needed. So this is the evaluation code, and the LLM cannot change it. And if the evaluator gave a good score to the algorithm, it is put into the program database again, and it continues again and again and again until reaching plateau and getting the best program. So, to conclude, the human defines what, and then AlphaEvolve creates this loop with prompt sampler, element sampler, evaluators pool, program database, and then again the prompt sampler. Any questions?
Why do you need to sample the prompt? So isn't the prompt the goal of the entire process? So for instance, in matrix multiplication, I want the prompt should be come up with an algorithm for more efficient matrix multiplication. And then
the prompt depends on the program. So it depends which program was sampled from the database. So it takes the program, it takes the goal as you mentioned, and it take the whole thing, the evaluator pools, and create this massive prompt.
So what is the difference between the goal of the entire process and the specific prompt? Can you give an example?
An example for prompt?
The difference of what is the specific prompt in a specific step inside this entire...
I will show it later. Okay, so AlphaEvolve uses two models, the Gemini Flash and the Gemini Pro. The Gemini Flash is mainly for getting diversity, many different algorithms for AlphaEvolve, and Gemini Pro is mostly to find the best algorithms, the best differences in the algorithm to get the best program. So let's go back to the matrix multiplication. We said that for 56 years they couldn't find a better algorithm, But here Alpha Evolve for 4x4 could solve it with only 48 scalar multiplications, which is crazy. And not just that, it also found better results for 12 other dimensions. This is an illustration, so here you can see the program, and Alpha Evolve with each iteration creates differences to the program. This is iteration 1 and 2 and 3, and then it compares it, evaluates it, and eventually, this is for the matrix multiplication, eventually after 15 iterations, it got its final result.
But how does it able to think of a new direction that were never thought before? Like maybe because it is like a trained model, so it uses what it knows already.
Think of it like mutations in genetic. It tries many different things. This is why the diversity of the programs. It tries many different things and then evaluate it and try to understand if it's correct, if it gets a good result.
He has like prior of what has already done. It's not like trying like entirely different thing that maybe this is what you need to get better results.
He's doing what he knows, but not necessarily in this algorithm. Like adding a different loss function. For example, here in the matrix multiplication, it added a new loss function to try to make a good algorithm with it, and okay, it succeeded.
But does it given in the prompt to try different things? Like,
what do you mean?
because if I just tell him solve like matrix multiplications in a better way than Strassen, so maybe just trying to do like what he knows, and I don't know, like.
He's trying to do what he knows, but in many different things, and like in different combination of things, and then he gets a new algorithm. Okay, so it sounds big, wow, it solved a major problem, but isn't it just like a sophisticated prompt engineering? Because first when we read the article, we thought, okay, so they just asked really nicely the Gemini, and it got a good algorithm. Okay, so what's new? And then we dived into it, and we found that there are major differences. For example, prompt engineering is mainly driven by human phrasing, and here there is machine feedback. The closed loop of Alpha Evolve without the human intervention consists of compiler and database and stuff that are not in like regular prompt engineering. Also, the memory in prompt engineering is the chat history, but here there is an external database with everything. And also, prompt engineering is based on manual review, but here you get automated debugging. So there is some kind of similarity, but there are also major differences that make Alpha Evolve work better. Okay, now let's look of some examples. Yeah.
Can I ask about the evaluators from before? Like, what is the evaluator? Say for the matrix multiplication, is it minimal number of operations?
Okay, so for the matrix multiplication, what the human defined is just like count of how many scalar multiplication. But also something cool that Alpha Evolve does is that it adds more evaluators. For example, for complexity or for other stuff. So this is why it's called like evaluator pool. It evaluates many aspects of the code and gets the best one.
And does it then usually fall to a kind of greedy search type thing? Because like I'm not going to make changes that make my code work for now, but maybe then another change will make it overall better.
What do you mean?
Like sometimes a bad change can later, like with another change, become very good. So maybe that's something that the model wouldn't ever find.
Like a change that it didn't reach to?
Something like that, yeah.
This is why it tries many different stuff. So we could see everything. Okay, so first example of something that Alpha Evolve. Second example if you look at matrix multiplication, but Google has this scheduler to schedule different tasks, like search and prompt and everything. It uses for Borg scheduler, and it used it for decades. This is like a regular manual scheduler, like Best Fit that you learned or something like that. And they tried to give it to AlphaEvolve to try to improve it. So what Borg does is like take a different job and different machines and try to find the best machine to take the job based on its memory and CPU requirements. So AlphaEvolve tried to take this function, they tried to match the job to the machine, and it created new, that looks super simple but actually very effective, a new function. Think of it like the Tinder for a job and machines. So here you can see, like what is a good score. Like the yellow is a very good score. They match good. They have nice kids, and purple is not good. So the output is a score, like a matching score between job and a machine. And they first did something really intuitive, like they tried to see the CPU residual and the memory residual. Each one is like the required divided by the free that the machine have. But they also added something not intuitive, like this is CPU residual and the memory residual. But they also added some penalty function that will penalty if the match is not good enough. It's like a convex function, I'm not going into this, but it's something that is not intuitive, but you can see and understand. And when they tried it on their resources, they found 0.7% improvement, which is a lot in Google scale. And it's actually in production, like they found it, and now they're using it. And there are big numbers saving $1 million that were saved thanks to this discovery of AlphaEvolve. Okay. Besides this, they tried AlphaEvolve on many different aspects. You see the data center optimization, but also other problems that they improved. And this was the computer science part, but we are talking about mathematics. So they also tried to take over 50 open problems in math in different fields: analysis, geometry, combinatorics, mainly focused on lower and upper bound. And 20% of the problems, AlphaEvolve found a better bound. And here you can see like an overview of many problems with the improved bound after AlphaEvolve iterations. Okay, again, sounds amazing, let's put it everywhere. But no, AlphaEvolve still has its pretty big limitations. First, it needs a fast machine verifiable evaluation function, and also it needs to be coded. So you can't take a big research problem and put it in AlphaEvolve, because it must be coded, fast evaluation for every part of the code, and also it is human dependent. AlphaEvolve is a closed loop, but still at first the human defines the evaluation function and previous algorithms and the prompts, so it still depends on human phrasing somehow and the human input. Questions so far?
How is it trained, or is there no training here, just using off-the-shelf LLMs?
Yeah, just taking Gemini Flash, Gemini Pro. This is the LLM part of AlphaEvolve, and also other parts that are not trained. For example, the evaluation function. Okay, we'll move to the next paper. So we've been in 2025 and now we're jumping to 2026. This paper is from 2 months ago. This is a paper towards autonomous mathematics research by, again, DeepMind. They control our lecture. Okay, but first, before I talk about the paper, I wanted to talk about Gemini DeepThink. It came out first at July 2025, approximately when Alpha Evolve was published. And I think this is the biggest advance in the field. So Gemini DeepThink, this is how they describe it in the DeepMind website. Best for modern challenges across science, research, and engineering. So no more Will Smith eating spaghetti. Now we want science. We want math problems. And Gemini DeepThink actually works amazingly. It reduces the compute time and has massive accuracy gain. We'll talk a little bit about what its innovations are. Okay, so first it uses parallel reasoning. Like instead of thinking about the best answer linearly, it simultaneously thinks about different paths of solutions and evaluates them and then give the best solution. It can merge different paths, so the solution is better. It also uses iterative development. It breaks some difficult problem into smaller steps and then evaluate them during its run. It uses 1 million token window. This is also true for Gemini Pro, but still worth mentioning. It integrates Google search and code execution tools inside the model, and also can process text, images, videos, everything all together. This is just like a visual example of Gemini DeepThink. So this is like a prompt of create a house, blah blah blah. So Gemini Flash created a house that looks like what I played when I was 6. And Gemini Pro created a better house and the trees are quite better, but Gemini DeepThink created much more detailed picture. Okay, so we saw before the break, if you remember, after the coffee of the break, that we talked about the IMO. So it was a big achievement to actually succeed in the IMO, but still there is a big difference. So the IMO, they use alpha geometry and all these constructions and the synthetic database and like many different things, combining with another like alpha proof that solved algebraic questions in the IMO. They got silver medal with a score of 28 out of 42. But later, using Gemini DeepThink, they achieved gold medal without constructions, just with Gemini DeepThink. So it's only 1 year apart, which is crazy. But still, now we want to actually solve research level questions. We don't want like a competition math, because it's more, competition math is more, it's bounded, we know that there is a solution, and research level math is open-ended problems that we don't even know if a solution exists. Competition math, you can like use symbols, but in research level math, you need it to be end-to-end in natural language. And also in competition math, the way you evaluate if you succeeded is like fail or pass. But in research level, you need experts, mathematicians, and like see if it's novelty and peer review. And sometimes it's like hundreds of pages of answers. So it's way more difficult than the IMO, even though the IMO was impressive. Okay, but there is still a major problem with using AI to solve research level math. It hallucinates a lot. It can cite papers that doesn't exist or cite papers that do exist but like completely wrong citations, and it's really hard to go through it. So Gemini DeepMind invented some engine called Alethea, which is powered by Gemini DeepThink, but also uses some circle of generator, verifier, and reviser. So it kind of looks like AlphaEvolve, just like an upgraded version. So as an input, it gets a problem, and then the generator creates some solution. It gets to the verifier checks whether it is hallucinated, something is off. If it's way off, then generate again. If it's just minor fixes needed, for the reviser to fix it, and then again to verify it, until we get a final output. Okay. So the core capabilities of Alethea is that it can admit failure. Like we're used to asking something the LLM, and it says yes, of course I know. But here, if it doesn't know, it said I don't know. And it also integrates web, Google search, everything. And which is very different from AlphaEvolve, it uses a natural language verifier. Okay, so its first milestone was that it's completely, fully autonomous created research paper. So there is this paper about eigenweights. I'm not going to dive into it, but using Alethea, it solved some kind of like something in this field, and also generated an entire paper that was actually published not so long ago. And the way it did it, it used like other field of mathematics. It used algebraic combinatorics, which is not related to eigenweights, but AlphaEvolve could, Alethea, or less Alpha, could find it. And this is like something from the paper. They add like declaration of AI usage, and they say that it was entirely generated by an internal reasoning agent, and the author's only contribution to this paper was exposition and introduction. Okay, another thing I want to talk about is, yeah.
Could I ask, so there was some fine-tuning for Alethea, for DeepThink to get to work with the hardness, or is it just, again, just plain?
Just plain, just Gemini DeepThink, but they use this loop of like generator and reviser, but yeah, besides just regular DeepThink. Okay, so they wanted to try to solve research level math, as we talked about. So we talk about Erdos problems. Paul Erdos was a famous mathematician, and he created this database of about 1,200 math problems. There is like a database that are all labeled open, like solved and unsolved. And when they created this paper, there were 700 unsolved Erdos problems. And they took all of those problems and fed it to Alethea and tried to see how many Alethea can solve. So, how many do you think Alethea solved out of the 700 open questions? So, who think A, 4 questions? Okay, 13. Okay, 63, 200. Okay, so most of you said 63. Let's see. Okay, so out of the 700 problems, 200 problems Alethea said that it correctly solved. The other, she said she couldn't find a solution. Out of the 200, only 63 were actually correct after they gave it to human to try to go over the solutions. But out of the 63 solutions, they gave it to really expert mathematicians, and they found out that sometimes AI get like when it doesn't really understand the question, or like it's some kind of ambiguous, it takes the easy path and it solved it correctly, but it's not what Erdos intended. So out of the 63 correct responses, only 13 were actually meaningfully correct, but out of these 13 meaningfully correct solutions, only 4 were actually novel solutions, because other were somehow existed in the literature. Some Aletheia said it existed, some Aletheia just solved, but later they found it in the literature, it just wasn't labeled solved in the database. So actually only 4, but 4 is a lot, even though it's not 200 or 63.
Can you go back a slide, please?
Yeah.
So the model claimed to solve 200 problems, but only 63 were actually verified externally. But the model has an internal verifier agent. So how come this gap that it misses like more than 50%? Like
It failed. The verifier couldn't verify it. It could for the other questions, but for these 137 questions, the verifier failed to say that it's not correct. Okay. So I still think that this is, yeah.
Wait, the verifier is also an AI?
Yeah.
Ah.
It's AI, but it's like different prompt. Like it needs to be objective. Okay, so this was Aletheia. It adds like major advancements and like complete new paper. And it was just 2 months ago, and when we got our papers, it was very new. But since then, much has happened, and maybe you heard, but just 6 days ago, as Adi mentioned, OpenAI said, "Oh my God, we discovered this new Erdos problem." They solved. They said that they not solved, but they found a counterexample for something in another Erdos problem. I want to talk about it a little bit, even though it's not in our papers, because it was really big. So they tackled a unit distance conjecture, which is problem number 90 in Erdos database. This is different from the other problems that I talked about, because it's like a more famous question, and maybe the 4 that it solved were kind of niche. This is how OpenAI markets their solution, but like try to think it yourself. Also, Erdos tried to he offered a prize for the one that solved it. So the question is, given n points on a plane, what is the maximum number of pairs that are exactly 1 unit apart? So Erdos said that the upper bound for the number of points is n times 1 plus O shell 1, O of 1. And they said that the grid is the best solution. And this was true for 80 years. Nobody could find a counterexample until 6 days ago, where OpenAI found a counterexample, and they showed that there could be n times 1 plus delta for some fixed delta points that are 1 unit apart. And I think the most interesting thing here is that they used general purpose reasoning model. They claimed they didn't use tool like Aletheia, which is revised. It's just the model, the general purpose model, wasn't trained on mathematics. And also here they got to the solution from a completely different field in mathematics. So it was really hyped. Wow, oh my God, amazing, milestone, wow, crazy. But still, there were some criticisms. For example, they said that, in October 25, also OpenAI said that they also they found solution for 10 Erdos problems, and then later they were all found in the literature. So they also claimed before that they solved, and they didn't really solve. also here they said it was completely with the model, but not really, because they still needed verification and refinement from experts here. And they didn't get like a full solution to the question. They just found counterexample, which is impressive, but it's not like the problem is solved. So now DeepMind and OpenAI try to like race each other and solve Erdos questions. I don't know if this was what Erdos intended when he created all of this database, but this was his future. So 2 days later, as Adi mentioned again, DeepMind said they solved another Erdos questions. And this is also only from the last week. So as you can see, it's super relevant, everything here, and it continues to change. Okay, so we saw that AI has many advantages. It can like give you solutions from different fields in math, which experts usually can't think about. It can go over all the literature, so it has like huge capacity of knowledge. Okay, cool, wow, AI is amazing, so are we all fired? Okay, not yet. There are still major limitations for AI as like a solo expert. It still hallucinates. It uses like reward hacking, as I said before. It takes the easy path if it can. You can't really sign LLM as an author because you need someone to take responsibility and like to be the stamp that said, okay, this is a correct and valid paper. And also it not yet can formalize like the next big questions in math. Okay, and now we'll go to the bonus part.
Yes. Do you have time?
It's like 5 minutes.
5 minutes. Yes, I just want to present. I will present the Lean tool, which I think is important and is connected to what Tal just said. That one of the limitations is the inability to formulate questions or to verify the solutions. If AI is now going to generate all of the new papers, somebody has to find out that it does not hallucinate. So Lean is a nice thing for that. You can see on top there is this very simple sentence. It's just a commutativity of multiplication. And it is proved with the relevant axioms, okay? And the nice thing is that you write something you want to prove. When you didn't finish to prove it, you don't get this nice V, and when you finished, you have this nice V. This is what's nice. And if all humanity agrees that this V, meaning true, then we can continue. And I just wanted to present this because I have a project with Oded Padon, who's here, and also Erez Lapid from mathematics. And we try to formulate something from a paper of Erez. Here is part of the definitions. This is a lemma. I didn't have enough time to edit this slide, but this is a lemma, and this is what happens when I tell Claude Code, okay, take the lemma, take the definitions, just prove. It can't do that. You can see there's no V, there's X, red X. So it's not that easy. There are things to do there. So I think it's interesting. And also Lean community is now exploding. You can look at the Zulip chat. It's a free thing, so it looks very. I mean, okay, don't do it. There's a little bit of drama there. If you want, you can ask me later. There is in Amazon. There's Leonardo de Mora who invented Lean. Google DeepMind use a lot of Lean. There are also 2 startups that are trying to formulate some mathematics with Lean, so they raised a lot of money. Yes, and also maybe it's interesting, the person that is behind Harmonic is one of the founders of Robinhood, this application for trading. So people from other subjects are now interested in this kind of things. And then I just want to show you the Goldbach conjecture. It's a famous one, right? Is it possible to represent every natural number with every even number as the sum of two prime numbers? So is it going to be possible to just write it into Lean and look and let Claude Code or Gemini Code CLI, whatever, prove it for us? I don't know, but it's interesting. It's been out there since 1742. So almost 300 years nobody can answer this very simple question that you can write in one line of Lean, just the definition of the question. Yes, so this was our presentation. Do you have any questions?
So basically, this project tried to develop a programming language for logic reasoning. No, the Lean project in general.
It tries to, in a way, I think, maybe Oded knows better, kind of create what maybe Gödel thought about. Some formal way to be able to say this is true, this is not. Write all mathematics in a formal way. So it is based on something called dependent type theory, which I'm not an expert of. But as far as I understand it, it's an IDE for the mathematical community to be able to agree upon statements, whether they're correct or not. So the first meaningful use of this thing, I think, was with the previous version of Lean, which called Coq, and could verify the four-color theorem. Yeah.
Just one question. You show in the second part that math is actually used as an evaluator of how well the model is or the agent is. So let's say Google DeepSeek wasn't really developed to solve mathematical problem, right? It was more generic and it was shown to be beneficial on math problem. And you show even that not only the evaluation, but also there is a research discovery in the math field. Was there any other research discovery in other fields using these models?
Besides math?
Yeah.
Actually, I don't really know. Really
I think
deep into math.
Yes, math is something that you can verify with just with the computer itself, right? If you want to verify some theory in biology, many times you need a
experiment.
Yes.
AlphaFold was gained a lot of attention for biology. I think there are.
But this is like an algorithm still. It's applicable for biology.
Other questions?
Let's
Okay.
speakers.